Have you ever heard of the pitch drop experiment? This experiment holds the record for being the world's longest running laboratory experiment. And in this experiment, all that we are actually observing is this black liquid that you can see in the funnel. This liquid is flowing into that beaker. So what's the big deal about this experiment? Actually, this black liquid, which we call as pitch, was poured into this funnel in 1927. And then for 3 years it was allowed to settle, and then in 1930 they cut the end of the funnel and allowed that liquid to flow down into the beaker. Now imagine what would happen if we had poured water into this funnel. The water would come gushing down and it would be collected into the beaker in a matter of seconds, because water flows very easily. But this liquid here, this black liquid which is known as pitch, actually doesn't flow easily at all. In fact, the first drop from the funnel into the beaker was dropped in 1938. And since then, only 9 drops have been into this beaker, which means it's very hard for this liquid to flow. And which is the property that is connected to the flow of liquids? That's the property of viscosity. This is one of the most important properties of fluids that we're about to learn. But before I move on to talking about viscosity, we will have to revise some concepts relating to liquids and fluids. And this is because we see that fluids are in general different from solids. And the first property that I want to talk about is pressure. Now, where do we think about pressure the most? In our daily lives, if I take a simple needle and try to push it against my hand, then I know that the needle will prick my skin and go inside. But instead of a needle, if I take something flat like a ruler, no matter how hard I push, it's not going to break my skin and go into my hand. Why does this happen? So these things in our daily lives convince us that not only is the force that you apply important, but it is also the area that the force is covering that is important, and from there stems the idea of pressure. And this force that I was talking about is nothing but the thrust. And by definition, it is the normal force exerted by a liquid at rest on a given surface in contact with it. So here we are talking about thrust exerted by a liquid, and there are 2 important points to remember about it. Thrust is just a normal force, that is the force acting perpendicular to the area that you are considering. And second, when you talk about the thrust of a liquid, you are considering that the liquid is at rest. And from thrust, we can move on to the idea of pressure. Now, thrust by definition is just the normal force acting on the surface. But luckily for us, liquids and gases exert a force on an object immersed in it, and they do so always normal to the object's surface. So by definition, all the force exerted by any liquid or gas, that is by any fluid, will always be normal to the surface, and therefore it will always be counted as thrust. And from here comes the idea of pressure. Pressure is nothing but thrust upon area, or I can say normal force divided by surface area. Now remember that even though the formula for pressure includes force, pressure is not a vector because it's not including the vector force, but actually just that component of force which is perpendicular to the area that you are observing. And in case of fluids, all force acting by the fluid is always perpendicular, that it is always normal to the surface, and therefore all the force exerted by a fluid is always a normal force. And this is the definition of pressure. It is simply the normal force per unit area. Now, pressure varies by one very important factor, and that is by height. If you take a look at 2 points inside any liquid which differ in height, then you should know that the point which is at a greater depth will have a high pressure exerted on it, and the point at a lower depth will have low pressure. And this is actually obvious. The point which is more deeper into the liquid will have more liquid above it to exert the pressure, whereas the point which is not so deep in the liquid will have less liquid above it to exert the pressure. So in general, we say that for a fluid column, pressure difference between 2 points which are separated by some height h is given by the formula rho gh. So P2 minus P1 is rho gh, where rho is the density of the fluid, g is acceleration due to gravity, and h is the height. The final point about pressure I want to make is that, as you can see, the pressure difference depends only on the height, and it is independent of the cross-sectional area, that means the shape of the container. All matters is that the height between them is h. But if pressure is changing with the height difference, then the next question is, if there is no height difference between 2 points, is there a difference in pressure? And that brings me to the concept of Pascal's law. Now, Pascal's law basically says that if the effect of gravity is neglected, then the pressure at every point of the liquid in equilibrium of rest is the same. So what does it mean by neglecting the effect of gravity? It exactly means what I'm trying to ask. If 2 points are at the same height, then the effect of gravity for these two is essentially the same. And therefore, for these 2 points, Pascal says that the pressure at both these points will be exactly the same. And from here, I can conclude that the pressure at all points on the same horizontal level in a fluid remains the same. And the only reason the pressure is changing from one level to another is due to gravity. But remember that Pascal's law is written down for a liquid at rest, that is in equilibrium of rest. So let's think about what would happen if we change the pressure on a fluid which is contained in a vessel. For example, if we have a flask which is fitted with a piston and 4 vertical side tubes of varying width connected to it, these side tubes are at different places on the flask and therefore have different heights. However, the pressure is indicated by the height of the liquid column in each of the vertical tubes, and initially it is observed that it is the same in all the 4 tubes, irrespective of their width or height. Now, if the piston is pushed, the fluid level rises in all of the tubes and remarkably reaches the same exact level in each of them. This indicates that when the pressure on the flask was increased, it distributed this pressure uniformly throughout the liquid. And hence, we come to the conclusion that the increase in pressure at one point of the enclosed liquid in equilibrium of rest is transmitted equally to all other points of the liquid and also to the walls of the container, of course, provided that the effect of gravity is neglected. This is Pascal's law. Now, this law accounts for the principle of transmission of pressure in liquids or gases. A number of devices are based on the principle of transmission, that is the Pascal's law. Famously, there are 3 hydraulic machines which use the principle of Pascal's law, that is the hydraulic press, the hydraulic lift, and the hydraulic brakes. Let's take a look at the working of one of them. For example, let's first consider the hydraulic press. In each of these devices, fluid is used to transmit the pressure. The hydraulic machines are based on the principle that a small force on a small piston produces a large force on a large piston. The setup of the hydraulic press consists of 2 cylinders, each fitted with a piston. The cross-sectional area of piston Q is much smaller than the cross-sectional area of the piston P. When the piston Q is pushed downwards, it exerts a force on the liquid. This force is converted into pressure, and this pressure is transmitted throughout the liquid equally according to Pascal's law. Because of this pressure, the liquid begins to flow from cylinder Q towards cylinder P. This causes an increase in the pressure on the piston P. Because of this increased pressure, the piston then exerts a force onto the bale of cotton, which then gets trapped and crushed between the piston and the fixed roof. Thus, a small force applied by a hand on the smaller piston was converted into a large force which was obtained from the larger piston. This is because the pressure exerted on the liquid at Q, which we will call as P1, is equal to F1 by A1, where F1 is the force exerted on the piston and A1 is the cross-sectional area of the piston. However, the force obtained, which we will call as F2, will be divided by the larger cross-sectional area A2 to give us the pressure of the liquid which it exerted on the piston. These two pressures, P1 and P2, are exactly the same according to Pascal's law, which means that F1 upon A1 is equal to F2 upon A2, and hence if F1 is small, the force obtained, which is F2, is increased by a factor of A2 by A1, which is also known as the mechanical advantage of the hydraulic press. Finally, if we want to bring back the hydraulic press to its original setup, the piston is then pulled upwards. This causes a drop in pressure in the liquid in cylinder Q. Due to this drop in pressure, the valve of cylinder Q pops open and liquid then begins to flow from the open vessel into the cylinder Q, restoring its original level. The excess liquid which had entered P also must be drained by opening the valve connected to cylinder P. Once this is done, the system is now back to its original setup. This is Pascal's law as applied to a hydraulic machine. Fluids have this really interesting property that is known as buoyancy. And you can see buoyancy in action when you watch as balloons rise up into the air filled with helium. You can also feel the action of buoyancy if you try to hold the string of a balloon and see that it's trying to tug its way out of your grasp and move upwards in the air. Similarly, you can watch a hot air balloon climb its way higher and higher as buoyancy helps it do so. So what exactly is buoyancy? Buoyancy, which is also known as the buoyant force or the upthrust, is nothing but the upward force exerted by a fluid on a solid immersed in it. Every time a solid is immersed in a fluid, it experiences an upward force. And this is evidence from the balloon in air or even, for example, a ship floating on water. The formula for buoyant force is given by V rho g, where V is the volume of the object, that is the solid, immersed into the liquid, and rho is the density of the liquid, whereas g is the acceleration due to gravity. So upthrust or buoyant force is given by the volume of the immersed object multiplied by the density of the liquid into the acceleration due to gravity. Thus, I can say that the buoyant force is directly proportional to the volume of the immersed solid, which means if I immerse half a solid, the buoyant force will be some number, and if I immerse the full solid, the buoyant force will increase. Similarly, the buoyant force is also directly proportional to the density of the liquid. There will be more buoyant force in case of a more dense liquid like say oil as compared to a less dense liquid like say water. And therefore, buoyancy depends on two factors: the immersed volume of the solid and second, the density of the liquid. And now we can understand the principle of Archimedes. The famous Archimedes principle says that when a body is immersed in a fluid, what happens is that it loses some of its weight. There is an apparent loss in weight of this body. In fact, we feel this when we try to go swimming. When we are floating in water, we feel less heavy than we actually are. So there is an apparent loss in weight of the body when it is partly or fully immersed in a liquid. And this loss in weight is equal to the weight of the liquid displaced by the immersed part of the body. A very simple demonstration can explain Archimedes' principle to us. Let's say I want to weigh what this solid is, so I use a spring balance and I note down the initial reading of the weight of this solid. As you can see, it is 800. I then immerse this solid into a liquid, for example water, and while I do this, the balance is still connected to the solid, which means now I am actually weighing the solid when it is in water. And when I do so, I see that the weight or the reading as shown by the spring balance has reduced. The new weight of this object as read by the spring balance is 400. So what exactly has happened? Nothing has happened. The weight of the object is actually still 800, but when the object has gone into the liquid, then the upward or the buoyant force has taken some of the load away from it, and that loss in weight or loss in load is what we are seeing as 400. Initially the weight was 800, now it's 400, so it has lost 400 in a loss of weight because it was immersed in the liquid. And this tells you that when objects are immersed in a fluid, there is a loss in weight, and by Archimedes' principle, this loss in weight is exactly equal to the weight of the liquid displaced. And therefore, if I want to find out the weight of the liquid displaced, it is simply equal to the volume of the liquid displaced multiplied by the density of the liquid multiplied by the acceleration due to gravity. And therefore the new observed weight, which is W dash, will be equal to the original weight W minus the buoyant force, because it is the buoyant force because of which that weight was taken away. So how much ever buoyant force is there, that much will be the loss in weight, and therefore sometimes the buoyant force is also known as the loss in weight of a body. Suppose I have a block which, when immersed in 3 different liquids, shows 3 separate observations. In one, it floats above the surface of the liquid, in the other it sinks straight down, while in the third it floats but beneath the surface of the liquid. This brings me to an important question. What decides what happens to a solid when it is immersed in a fluid? How can we tell whether it will float or sink? The answer to this lies in the law of flotation. The law of flotation basically says that a body will float in a liquid if the weight of the liquid displaced by the immersed part of the body is at least equal to or greater than the weight of the body. To demonstrate this, let's observe what's happening to the block when it is immersed in the first liquid. In this case, the block floats above the surface of the liquid. I now measure the weight of the block in comparison to the weight of the liquid displaced by this block, and I find that in this case, the liquid displaced is greater in weight than the weight of the block. And therefore, this tells me that if the liquid displaced is greater in weight than the weight of the object, then the object will float above the surface of the liquid. However, as is seen in the second case, the object sinks, which means that the weight of the object is greater than the weight of the displaced liquid. And finally, in the third case, the weight of the liquid displaced is exactly equal to the weight of the object, and therefore the object floats but within the liquid. This is known as the law of flotation, and it helps us decide whether an object floats or sinks inside a fluid. So now we can go back to the pitch drop experiment and try to answer the question, what is so different about that black liquid, that is the pitch, that was causing it to flow so slowly? And the answer to that is viscosity. Viscosity is present in almost all liquids. This is because when they flow, even though it looks like it might be easy for them to flow, actually they are experiencing some internal friction between their layers. And this is known as viscosity. The property of a fluid by which it opposes the relative motion between its different layers is known as viscosity, which means that one layer is trying to stop the other layer from moving, and therefore overall, because of viscosity, the liquid is experiencing an opposing force to its motion. So this opposing force to the motion of a liquid is known as the viscous force, and this phenomenon is viscosity. This is almost like the friction that a solid experiences when it's trying to slide along the surface. This property of viscosity is responsible for why some liquids flow faster while some liquids flow slower. And to formulate this viscosity property, we have Newton's law of viscosity. Newton said that the viscous force, which is nothing but the retarding force, is in any layer is directly proportional to the area of that layer and to the rate of change of velocity with distance, which is also known as the velocity gradient. dv by dx is the velocity gradient. And from this I get the constant of proportionality eta, which is known as the coefficient of viscosity. Now, whenever an object heavier than a liquid is submerged inside it, then that object sinks. But how fast the object sinks or how much time it takes for that object to reach the bottom of the container depends upon viscosity. This is known as Stokes' law. An object falling through a fluid experiences an opposing or a retarding force which decides how much time that object will take to sink to the bottom of the container in which the liquid is placed. And this force, the magnitude of which is given by Stokes' law. Stokes' law says that the viscous force acting on a small sphere falling through a medium is directly proportional to the radius of that sphere, to the velocity with which it's falling through the fluid, and to the coefficient of viscosity of the fluid. So mathematically, I can say that the viscous force F is directly proportional to eta, r, and v. Keep in mind that Stokes' law is only defined for a small sphere because it's a very nice regular shape. Trying to understand the viscous force acting on an irregular shape is difficult and beyond the scope of this video. And therefore Stokes' law is only going to keep in mind a small sphere of radius small r, and it says that F is proportional to eta rv. But when this object is falling through a liquid, it is important to note that its velocity initially goes on increasing, which means that the object is initially accelerating. And this is happening because of the effect of gravity. But if you look at the forces which are acting on this object, you have the buoyant force acting upwards, the viscous force also acting upwards because it's retarding its motion, and you have the weight of the object pulling it downwards. At some point while the object is falling through the fluid, it will reach a point where the viscous plus the buoyant force will be exactly equal to the weight of the body itself, and in such a case then the object will start falling with a constant velocity. It will no longer have an acceleration, and this final constant velocity with which that object sinks through the liquid is known as the terminal velocity. What actually happens is that when the object is falling through the fluid, it is taking along with it the layer of the fluid which is in contact with the object. Because of this, there is relative motion between the layers of the fluid, and a viscous or an opposing force is set up. This viscous force is what is exactly opposing the motion of the object, in our case a small sphere, through the liquid. And like I said, at one point, the viscous force and the buoyant force end up balancing the weight of the body, and at such a point in the motion of the object through the liquid, at such a point the velocity becomes constant, and then the object falls through with this constant velocity, and this is known as terminal velocity. It is given by the formula 2 by 9 r square rho minus sigma into g divided by eta. Here r is the radius of the sphere, rho is the density of the sphere, sigma is the density of the fluid, g is the acceleration due to gravity, and eta is the coefficient of viscosity. What I want you to notice is that so far, before we started studying about viscosity, we were talking only about liquids at rest. But with the idea of flowing liquids comes the idea of viscosity and terminal velocity. And hence now we are talking about concepts related to the flow or the motion of fluids, and this is nothing but fluid dynamics. Another concept vital to the study of fluid dynamics is the concept of the type of flow of a liquid. Liquids don't always flow in the same way. This is evidenced by the fact that if you go to your kitchen tap and open the tap just a little, the water you will see is flowing smoothly. However, if you open the tap completely, the flow of the water changes, it becomes irregular. And in fact, sometimes the water even splashes upon you. So there is definitely a difference between opening the tap just a little and opening it completely, and the difference lies in the type of flow that the water is undergoing. And therefore, this brings us to the types of flow. Whenever a particle is moving inside the fluid, that is, a fluid particle is moving, it will describe some path, and this path which is taken by the particle in a fluid is what is known as the line of flow. And the tangent drawn to this line of flow will tell us the direction in which this fluid particle is tending to move. Now, the first type of flow that we will see is known as the streamline flow. The streamline flow is also analogously known as the laminar flow. By definition, it is the flow in which each element of the liquid which is passing through a point travels along the same path and with the same velocity as the preceding element passing through that point. Let's take a look at what this means. If we observe the flow of the liquid at a particular point, we'll see that every particle in the streamline flow passes through this particular point with the same velocity. This doesn't mean that every particle has the same velocity. In fact, after passing through the point, the velocity of the particle may change. But if I'm looking at a single point in observation, then every particle that is passing through this point will follow the same path taken by the previous particle and will also have the same velocity as it passes through that particular observational point. The path taken by a fluid particle in a streamline flow is called a streamline. and the motion of the fluid is thus represented by streamlines. Streamline flow is also known as a steady flow. At any point on the streamline, a tangent indicates the direction of motion at that point, as already discussed. No two streamlines cross each other. If you take the cross-sectional area of a fluid in flow and draw the streamlines at the periphery, what you get is a tube of flow. As streamlines do not intersect, fluids flowing through different tubes of flow do not mix with each other. Thus, they are separated from each other even though physically there is no barrier between them. So this brings me back to the example where when I opened the tap in my kitchen completely, I saw that suddenly the smooth flow went to a chaotic or an irregular flow. And therefore, we can think about this and come to the conclusion that this must have something to do with the velocity of the fluid. And this brings me to the idea of the critical velocity. The velocity of a liquid up to which its flow is streamlined is known as the critical velocity. Above the critical velocity, the flow becomes turbulent. The formula for the critical velocity is given by Vc is equal to nr eta upon rho d, where nr is what is known as the Reynolds number, which is unique to the type of liquid. Eta is the coefficient of viscosity, rho is the density of the fluid, and capital D is the diameter of the tube through which the flow is taking place. Thus, critical velocity is essential to understand at which point will the flow become turbulent. And therefore, with the idea of critical velocity, I can define what is known as the second type of flow, which is the turbulent flow. And then, simply speaking, the flow in which the liquid moves with a velocity which is greater than the critical velocity, this flow will be known as the turbulent flow. In such a flow, the motion of particles is irregular or disordered. And thus, the two types of flow that we have studied are the streamline or the steady flow and the turbulent flow. The quickest way to find out whether a liquid will undergo a streamline or a turbulent flow is to look at the Reynolds number. Reynolds number is basically just a pure number which determines the type of flow or the nature of flow of liquid through a pipe. And we use the Reynolds number, which is denoted by n subscript r, in the formula for critical velocity. And hence here we can write the formula for the Reynolds number by reversing that formula, and I get that nr is nothing but Vc rho d by eta, where Vc is the critical velocity, rho is the density of the fluid, capital D is the diameter of the pipe, and eta is the coefficient of viscosity. And thus you can see that the Reynolds number does not depend upon the system of units. By definition, it is the ratio of the inertial force per unit area to the viscous force per unit area. Thus, looking at the Reynolds number, we can tell whether the liquid will undergo a streamline or a turbulent flow. For example, here, while looking at the red liquid which is being injected into this pipe, we see that for the initial part of its motion, the flow is streamline. However, when the cross-sectional area of the pipe is reduced, then at the intersection, the flow turns turbulent. And therefore, I can say that the Reynolds number for the first portion of this flow lies between 0 to 2000, meaning that this flow is streamlined. However, after the intersection, the value of the Reynolds number changes such that the flow is now turbulent. Now, fluid flow in general is a very complex phenomenon. But one of the most important properties, which is the pillar of fluid dynamics, is the Bernoulli's theorem. The Bernoulli's theorem is nothing but a statement of the law of conservation of energy. We already know that objects have potential and kinetic energy, but liquids have what is also known as the pressure energy. And Bernoulli's theorem is basically saying that the sum of these three, that is pressure energy plus potential energy plus kinetic energy, is a constant. And actually, it is just a statement that says that the total energy per unit volume is constant. And from this, we can write the Bernoulli's theorem, which states that for unit volume of liquid flowing through a pipe, I can say that P plus rho gh plus half rho v square is always a constant. That means the sum of the pressure plus rho GH plus half rho V square written for any cross section throughout the pipe will always be a constant. If I consider a fluid moving in a pipe of varying cross-sectional area and I apply Bernoulli's theorem to the two ends of the pipe which have different cross-sectional areas, I will find that the sum of the pressure, potential energy per unit volume and kinetic energy per unit volume at one end of the pipe which has a lower cross-sectional area is exactly equal to the sum of the pressure, potential energy per unit volume and kinetic energy per unit volume at the other end of the pipe which has a higher cross-sectional area. And therefore I will get that P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. This is Bernoulli's equation. Note, however, Bernoulli's theorem does not consider the energy loss due to friction. In practical situations, however, there will always be some energy loss during the flow of a fluid. Another fundamental principle related to fluid dynamics is the equation of continuity. Have you ever wondered what happens to the speed of a liquid as it flows through a pipe of varying cross-section? Since tubes of flow do not intersect, the mass of a fluid entering a given tube through any cross-section of the tube in a given time interval is always equal to the mass flowing out through any other cross-section in the same time interval. In simple words, the equation of continuity tells us that if you have a pipe of varying cross-section, and let's say at one end the cross-section is large, while at the other end the cross-section is small, the speed with which the liquid flows through these cross-section will be different. The equation of continuity is nothing but the statement in the conservation of mass. And thus, on observing the liquid flow through varying cross-sections, it is found that liquid flows with a higher speed in a narrower cross-section, whereas it flows with a lower speed in a wider cross-section. Mathematically, then, we can say that the equation of continuity, which is a statement in the conservation of mass, is basically saying this, that in case of a non-viscous fluid in a streamline flow, while it passes a tube of varying cross-section, the product of the area of cross-section and the speed with which the fluid crosses that section is a constant. And therefore, I can say that A and V are inversely proportional to each other. The product AV is known as the volume flux or the rate of flow of the fluid through that cross-section. Thus, equation of continuity is simply saying that in cases where the cross-section is narrow, the fluid velocity is faster and vice versa. The rate of flow of a liquid through a horizontal capillary tube, that is the volume of the liquid flowing per second, is given by the letter capital V, and this is given by Poisson's formula, which says that V is proportional to P r raised to 4 upon L eta, where P is the pressure difference, r is the radius of the pipe, L is the length of the pipe, and eta is the coefficient of viscosity of the fluid. The constant of proportionality in this formula is pi by 8. Thus, we have learned three very fundamental principles relating to fluid dynamics, that is the Bernoulli's theorem, the equation of continuity, and finally Poisson's formula for the rate of flow of a liquid. Keep in mind that Poisson's formula is only in case of a steady flow where the fluid is flowing through a horizontal capillary tube only. Similarly, the equation of continuity is valid for a non-viscous fluid, again in streamline flow. One of the applications of Bernoulli's theorem is the explanation of liquid flow from an open tank. Consider a tank containing a liquid of density rho with a small hole in its side. The liquid flowing from this hole will change in speed as the level of the liquid in the container drops. This change in speed is due to the change in pressure. The word efflux means fluid outflow. Torricelli discovered that the speed of efflux in an open tank is given by a formula similar to that of a freely falling body. The speed of liquid coming out through a hole at a depth h below the free surface of the liquid can be given by Torricelli's law. Let V1 be the speed of the fluid coming out from the orifice, and PA is the pressure of the atmosphere. H is the depth at which the orifice lies from the free surface of the liquid. Let the pressure of the liquid at the free surface inside the container be capital P. From Torricelli's law, then the speed of the liquid flowing out of the orifice is given by root 2gh plus 2 P minus PA divided by rho. When the pressure P at the free surface of the liquid is much greater than the atmospheric pressure, the speed of efflux is determined by the container pressure only. However, if the tank is open to the atmosphere, then P is equal to PA and V1 is equal to root 2gh, where h is the depth of the orifice from the free surface of the liquid. This is the speed of a freely falling body. A ball which is thrown up in the air while falling down under the force of gravity alone will fall down with this velocity, which is given by root 2gh. And thus Torricelli said that in case of a fluid flowing out from the orifice, the speed will be similar to that of a body which is freely falling under the effect of gravity alone. So this wraps up the concepts that I want to revise under the properties of fluids. Thank you for watching this video. If you like our channel, please click on the subscribe button here. And if you'd like to get your very own Target Publications book, you can click on the link here. Please keep watching our channel for more updates.